Okay, situation of diagonalization is fairly simple if you've got everything else. And there's some real advantages to it because the matrix is diagonal. It's really easy to multiply by it. Okay? So diagonalization n by n matrix, which you can think of as representing a linear transformation. Okay? If there are n distinct eigenvectors, eigenvalues, then you get n distinct eigenvectors. I didn't write the word distinct, and I should have, but you can read. Okay? Let B be the basis of eigenvectors. Then your transformation relative to that basis B is represented by a diagonal matrix. Okay? And you know how to do the change of basis. Okay? So you get your your diagonal matrix is just P inverse AP, where P is your change of basis matrix. Okay? That's all. Now, when I say that's all, there's some details around this, but that's not a difficult idea. Because we've already been through change of basis, you know how to do change of basis. And hopefully you've understood what I've told you about the meaning of change of basis. Okay? So, that's the first thing you got to know about diagonalization. Now there's a little more, because even if you don't have n distinct eigenvalues, you can have a repeated eigenvalue. Now that repeated eigenvalue, when you plug that eigenvalue in and get your simultaneous equations, you might find that they reduce just down to one equation, in which case you've only got one eigenvector for that repeated eigenvalue. Okay? But you could reduce that down to two equations and get two eigenvectors, right? So if you've got a repeated eigenvector, you might or might not get repeated, you get a number of eigenvalues, right? So if an eigenvalue repeats in your characteristic equation, that means like you got an x minus 1 squared in your characteristic equation, or lambda minus 1 squared. Lambda could be 1, but it has a multiplicity of 2. That's important. Because then you might or might not get two different eigenvectors. So this may or may not result in multiple independent eigenvectors, okay? And I'll put the word linear because independent kind of implicitly in this context means linearly independent, but let's be explicit, okay? Now, does that halfway make sense? I mean, you know when you plug your lambda into your simultaneous equations that you get out of your, you know, the A minus lambda I matrix, okay? If you have distinct eigenvalues, then every lambda that you plug in is going to reduce whatever those equations are to 1. They're all going to be multiples of each other, okay? If you have a repeated eigenvalue, it's possible that that's not going to happen. If it repeats twice, it's possible you're going to get 2 independent equations. You have a free variable, and you get 2 different possible eigenvectors, okay? And maybe 12 independent eigenvectors from a repeated, from an eigenvalue that has multiplicity 12, okay? So it can happen, but it doesn't have to happen, okay? And we could say,
Let's talk about your side projects really good. So, side projects overall look very, very well done.
so you may or may not get what we call a full set. We may or may not get a full set, i.e. we may or may not get n linearly independent eigenvectors. And if we don't get n linearly independent eigenvectors, then we don't have a basis of eigenvectors, so we can't diagonalize the matrix. So if not, we don't have a basis. Of eigenvectors. So we can't diagonalize.